in our online meeting, we started talking about two important combinational circuits. One of them was encoder, and the other one that we will talk about today is decoder. These are inverse operators. Okay? What does that mean? That means if you encode data, you get some output, and then you use that data to decode and then get back the same data that you originally had. Okay? So we use encoders, okay, to assign a code word to a potential possible outcomes of an experiment set. Okay? For example, I give you an example in our online meeting that we have those buttons in our phones, right? One, two, three, four, five, 6, 7, 8, 9, and then 0. You got 10 digits, and when you push one of those digits, there's an electric circuitry behind, okay, that senses, okay, that pressure. So it creates, so these are all connected to wires, right? And when you push, for example, 5, this would close the circuit that is connected to 5 volts, usually, and creates a digital 1, and the rest of them are all zeros. Okay? That's what's exactly happening when you push a button on your phone, keypad. Okay? So what that means is that there are 10 of those, right? And there's only one of them is 1, the rest are 0. Unless you push, 2 buttons at the same time. But that usually doesn't happen. Okay? So this is exactly the input you expect to an encoder. So encoder expects, all encoders actually expects, only one of the inputs to be 1, and the rest of them are to be 0. And what is the output? The output is the code word you assign to that particular outcome. Okay, one of those buttons in this case. What does that mean? That means, for example, let's suppose that there are 4 buttons, okay, for this particular encoder, okay, 4 by 2. And only one of them is 1, for instance, this one, and the rest of them are 0. An encoder generates the code word that corresponds to this one, which is the top one, and we usually use binary encoding, remember? Binary encoding, unless this encoder is something else, some other encoder. But we usually use binary encoders, so this would correspond to 00, 01, 10, 11. Throughout the course, we will use always this kind of mapping. So therefore, if encoder sees a 1 in the top input, that means it's going to map it to 00, so the output would be 00. This is the most significant bit. This is the least significant bit. All right? So it's pretty easy functionality, as you can see. If this was 1 rather than 0, and this needs to be 0 then, right? Then this would be pushed out as an output. Okay, so the encoder's output would be, in that case, 0, 1. The most significant would be 0, least significant would be 1. Okay? So on and so forth. That's the encoder. That's the general description of encoder. Okay? And I also talked about one more thing in our online meeting. So I'm trying to, create a summary of what we have already talked about, just to refresh your mind. The second thing I talked about was, again, an encoder, but I've got a special name for that encoder called priority encoder. Remember that discussion? Priority encoder? What does that mean? Priority encoder actually looks at specific inputs that are not valid, such as 1010. That's not a valid input. Because we expect, the general description of encoder expects only one of the inputs to be 1, the rest of them are to be 0. And that happens, for instance, when you are trying to, push those buttons to call a number, for example, and you accidentally pushed 2 buttons at the same time, maybe. Okay, so that would create some mistakenly typing numbers, and those need to be dealt with by the encoder. This encoder cannot do anything about that input, because that input is an invalid input. Okay, so that's why people came up with the idea of priority encoder. In the priority encoder, you still have this encoder. Okay. And you got 4 inputs, of course. And there are 4 inputs here that are valid. That means you got 1, 0, 0, 0. So let's just name them. So that would be actually a good practice to name inputs. D0, D1, D2, D3, let's say. Or maybe you can use E. That might be maybe more appropriate here, because we're talking about encoders. So let's just use E. E0, E1, E2, E3. So that means this is E0, E1, E2, and E3. Please interrupt any time when you have a problem or a question. Okay? So these are the valid inputs: 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay? And apparently these are just only 4 out of 16 total number of possibilities. There are 16 of them, but we only treat 4 of them to be a valid sequence. So these are valid. How about in priority encoder? Priority encoder, every input is valid. Every single potential possible 4-bit combination is a valid input for priority encoder. Okay, unlike the general description. That means, for example, let's just say again, these are E0, E1, E2, E3, E0, E1, E2, and E3, 0, 0, 0, 0, up until 1, 1, 1, 1. Okay? All of them are possible valid input. However, how are we going to generate 2-bit output? Because you can only, as you know from if you remember when we talked about in the first 2 weeks, we talked about representations, right? Data representation. And we talked about encoder there, actually, maybe implicitly. But we know that if you got 4 numbers, you should use 2 bits to represent any one of them, right? Or if you got 8, for example, numbers, you need 3 bits, at least 3 bits to represent those numbers. Okay, so in this case, you got 2 bits to represent. That means you can only represent 4 potential inputs. Okay, so these are the ones that you are mapping, for example, to this one to 0, 0, this one to 0, 1, this one to 1, 0, this one to 1, 1. But you've got 16 of them here, and you got only 4 potential outputs. Okay, so the question is, how are you going to map them? Because apparently some of them would map to the same thing. All right? So the logic here, as the name implies, you have to take into account the most significant one only. This is actually telling you how the mapping is done. Okay? So you basically look at from left to right, because this is the most significant bit and this is the least significant bit in my definition. Okay? Therefore, if you go from left to right, whenever you see 1, that is your 1 in here. Okay? You only take into account the leftmost one to be your actual one. The rest of the ones are going to be treated as, error. Okay? That's just the description of the priority encoder. So therefore, let me just give you an example. Let's just consider this one, 0, 1, 0, 1. What would that be mapped to in this priority encoder context?
The second one is E1.
Let me just write down the mappings here so that you can tell me exactly which one. Okay, so these are inputs, and let me just this to be O0, and this is O1, O0, O1. Okay, so this is mapped to 0, 0, 0, 1, 1, 0, 1, 1. So my question is, what would that be mapped to in the priority encoder context? So I expect 2 bits.
I think 0, 1, 0, 0, 1.
0, 1?
Yes, sir.
0, 1?
0.
Everybody agrees with 0, 1. Why? Because, as I said, the logic is simple. You start from here to here because you treat this to be most significant bit and this to be least significant bit. Sometimes you may treat this to be most significant and least significant, depending on how you define them. But I define E0 to be my most significant. In that case, you start from left to right, go from left to right, and you basically search for a 1. So you basically, when you figure out that 1, which is the first one from left to right, that is the real one. The rest of the ones are going to be ignored. Okay? So which means this will be ignored. This will be actually treated as a 0. So therefore, this is 0, 1, 0, 1 in this table. If you look at this 0, 1, 0, 0 in this table, you will see that this is mapped to 0, 1. So therefore, the code that you map to this input would be 0, 1. This is your most significant bit. This is your least significant bit. Okay?
So,
0, 1.
can I ask you a question?
Yes?
So, if you put 5 and 8 on your phone,
Yes, 5,
and
8.
if your phone has priority encoder, should 5 will be?
Yes, I mean this
Sure.
this is only for 4 inputs, of course. But
Okay,
if you think about 10 inputs case, yes, this would actually correspond to. In this case, you would take 8 because 8 has got. This is a bigger number, so this has got a more,
yes,
more significant bit of 8 is going to be closer to the left hand side,
So,
right? So this 8 is if you push 5 and 8 in any order you like. The priority encoder will get it as 8, not 5.
It's not about time, it's about the most
Significant, yes. So it takes the bigger number actually in the decimal domain. Okay? It takes the bigger number. But as I said, this is again open to question whether this is the most efficient way of implementing encoders, or maybe it is the most efficient. Is it the most efficient way of mitigating the error? Right? Well, that's open to discussion. I'm just describing a specific description of a circuit, okay, of an encoder that works this way. If you believe that there might be another encoder out there that is more efficient than this or better in terms of failure tolerance, well, go ahead and implement it. But what I'm just focusing on here is a specific example that is known by the community, which is called priority encoder. And I'm going to show you, how we implement this, okay? And we actually did this, so I'm not going to go into the details. But in our last meeting, in our online meeting, we talked about this, and I came up with some Boolean expressions, if you remember. Those Boolean expressions actually belong to the analysis of the truth table that belongs to this priority encoder. Okay? So in other words, if you do all these mappings, you will realize that you can draw the Karnaugh map that corresponds to, for each one of these outputs, you can draw 2 Karnaugh maps, okay? Since we've got 4 inputs, okay, that means you have to deal with 4x4 Karnaugh maps. But since you know the mapping, actually, you can actually create a truth table, okay, for each one of them, O0 and O1. So you can go ahead and implement this using this column in your Karnaugh map, and then this column in your Karnaugh map, do your simplifications, and you come up with a Boolean expression. Okay, the rest is just the general analysis tools that we already have, and the minimization tools we already have. And you may also want to look at whether or not there is a cross optimization opportunities. Maybe there are some common terms between these two. Okay, that might be a possibility. But anyway, the rest is just standard. So that's why I'm actually more focusing on the description of of the design example, because this is a design example, okay? So somebody, even if you didn't know the priority encoder, somebody could give you the description of that encoder and expect you to design that, okay? But the design part is just standard. As long as you understand the description, the design part is just simple. Anyway, so this is encoder. This is priority encoder. What I want to do is today, I'd like to talk the rest of the apple, right? The decoder. Okay, it's pretty simple because if you understand the encoder, the decoder is kind of straightforward because it's just a reverse, functional reverse operation. Okay, so instead of having 4 inputs now, you have 2 inputs now, right? The code. Somebody gives you the code and he wants you to figure out the outcome, right? And these are going to be named as D0, D1, D2, and D3. Okay, here's the truth table. Now there is no possibility of having an invalid input because I'm going to actually span all the inputs. All right, 0, 0, 0, 1, 1, 0, 1, 1. Okay, and these are my outputs, D0, D1, D2, D3. If you got 0, 0, then the decoder output would be D0 being equal to 1, and D1, D2, D3 are all zeros. Okay, so this is 1, 0, 0, 0. Similarly, if A0 is 0 and A1 is 1, then D0 would be 0, D1 would be 1, D2 would be 0, and D3 would be 0. Okay? And similarly, D2 and D3 would be 1 corresponding to these input sequences. Remember now, encoder is exact reverse. The decoder is exact reverse of the encoder. Okay? It's a 2x4 decoder. Okay? And since the circuit generates now these outputs, right, we assume them to be, okay, we assume that, for instance, 0, 0, 1, 1 would never appear because we design our circuit that way. All right? So we don't need to now worry about the errors that we had in the encoder because this was our input. Okay, so if you look at now the D0, for example, so this is my D0, right? Let's just look at the Boolean expression that corresponds to this D0. Okay, there is only 1, 1, and the rest of them are 0. So there is no need to group things. Like if you remember my Karnaugh map, you don't even need to draw the Karnaugh map because there is only 1, 1, and that corresponds to the mean term that for A0, 0, A1 equals 0. What is that mean term? A0 prime and A1 prime. So in fact, D0 equals A0 prime and A1 prime. Okay? Because there's only 1, 1. So I'm actually treating every one of these D's as functions, right? Because D0 is a function of input, D1 is a function of input, D2 is a function of 2 inputs, and D3 is a function of these 2 inputs. Okay? And I'm going to find Boolean expressions that corresponds to these outputs in terms of inputs. But it's very simple because each one of them actually corresponds to a single mean term. You see, this is going to correspond to this mean term, this is going to correspond to this mean term, and this is going to correspond to this mean term. Okay? So D0, D1 equals A0 prime A1, D2 equals A0 A1 prime, and D3 equals A0 A1. Right, these are the corresponding mean terms for each one of these outputs. So decoder actually can be used to output mean terms, right? So it makes it very simple to implement any function, not just these, but if, for example, want to implement F0, 1, 1, 0, for example, then all you need to do is to collect these 2 mean terms. But these 2 mean terms are what? D1, right, and D2. So F actually equals to D1 plus D2, right? This is OR, of course. Right? So all you have to do, if you would like to implement a function, f, any function actually, so all you have to do, you basically put A0 here, A1 here, and then D0, D1, D2, D3. This is a decoder, of course. Okay? Then this says, just collect them, collect the midterms from the output of the decoder, and then OR them together to find your function f. Note here that if you are supposed to use a decoder to implement a function like this, you may have to use sometimes AOI gates, extra AOI gates, along with the decoder. Okay? So decoder plus some AOI gates. But of course, you would like to minimize this, right? Because the main purpose is to use decoder in your design. All right? Okay. So I've shown you a decoder by 2x4, and sometimes you would need bigger decoders, okay? For instance, 4x16, okay? Or 3x8, okay? So the question is, how are we going to get to these bigger designs? Because when you go to market, if you want to buy a decoder, they come in standard form most of the time. What that means is that if you go to market and you would like to buy a specific decoder, say 5x128 size, okay, you may not find this. So you may find 2x4s, maybe, or maybe 4x16, okay, but not this one, okay. So therefore, you're gonna have to do something about it. And the design says, so there we have the hierarchical design come into play. Okay? The hierarchical design that I mentioned about it in our online meeting, if you remember. So in this case, what you expect, for instance, we'll come to this one, but let's just suppose this one is what we want to get using 2x4, two 2x4 now, right? 2x4 design. So if you have, this is your first decoder, and this is your second decoder, right? And you got 4x16, right? So you need A0, A1, A2, and A3, 4 of them. So A0, A1, A2, and A3. So I know the decoder's general description. If you have A0, A1, A2, and A3, what is the first output? The first output, let's just put the outputs here. If you have A0, A1, A2, and A3 as input to this 4x16 decoder, what would be the first output, which is the first mean term actually? In other words, M0, right? Because this is M0. M1, M2, M3. Remember the notation we used for the midterms? Similarly, you would have the exact same idea. You will have M0, M1, M2, M3 up until M15 here. Do you remember what M0 is?
A0 prime, A1 prime, A2 prime, A3 prime.
Absolutely. A0 prime, A1 prime, A2 prime, and A3 prime. And what is the final one? Exactly. A0, A1, A2, and A3. Okay? So you have actually all these mean terms starting from 0, 0, 0, 0, ending with 1, 1, 1, 1. That is the corresponding binary sequence to that mean term. Right? That's why I wrote them underneath. Okay, now, I'd like to get the first output. What should I do? Let's just look at the outputs of the decoders. The first output of this decoder, A0, A1, is, as I already mentioned here, A0 prime, A1 prime. And this one is A0 prime, A1. This one is A0, A1 prime. And this one, the final one, is A0, A1. Similarly, for this decoder, I've got A2 prime, A3 prime, A2 prime, A3, A2, A3 prime, and A2, A3. Okay, so I'd like to get this mean term at the outputs. I look at this, I got A0 prime, A1 prime in the first, this top output of the first decoder, 2x4. And I also have A2 prime, A3 prime is at the top output of the second decoder. So why don't we just AND these two? Because if I AND them, I got A0 prime, A1 prime, A2 prime, and A3 prime, which is exactly what I'm looking for. Okay? And actually, idea is the same. If you'd like to get the second, for example, midterm, M1, help me write it. A0 prime, A1 prime, A2 prime, A3, right? So therefore, this A0 prime and A1 prime, again, will come from the same outputs. However, now you connect an AND gate to the next output of the second decoder in order to get A2 prime and A3, because you got A2 prime, A3 in your midterm expression. Okay? Therefore, I'm going to take this and then take that one and them, and you got A0 prime, A1 prime, A2 prime, A3. And let's just come back to the final midterm, which is A0, A1, A2, and A3. Okay? You got A0, A1 here, A2, A2 here, so why don't we just AND them? And you got A0, A1, A2, and A3. And you do all of them just like this. You connect them, you go through all combinations, you select one from here and one from here, and you connect them. And there are 4, and 4 here, 4 by 4 gives you 16 different possible combinations, and you've got 16 outputs in that way. All right? So therefore, you design now, if you just put these wires a little bigger, you will realize that you can now, this bigger circuit now is your 4 by 16 decoder. All right? This is hierarchical design. We did not, for instance, apply our design logic based on kernel maps, AOI gate technology. This is a different design because now you're using smaller blocks to come up with a bigger block that does exactly the same thing, but number of inputs and outputs are higher, bigger. All right? Of course, you always have, as you can see, similarly in here, a function implementation. You may have to use extra AOI gates. In this case, we used AND gates, and we got 16 of them. Okay? If you ask me, rather than using hierarchical design just like that, if we had a computer software, okay, and I give the truth table to the computer software because I've got 4 inputs, which makes 16 rows in my truth table. And I define each one of these outputs, 16 of them. Okay? Think about the size of the truth table you would have. 4 inputs and 16 outputs. Okay? So that would give you 16 by 16 plus 4, right? Which is 20, right? That big of a matrix full of zeros and ones, right? And you apply, because it's a computer software, you tell the computer, run the kernel maps for each one of the outputs and come up with AOI logic, and then figure out the common terms between them, and then minimize the circuit as much as you can. You would probably get a simpler logic compared to this one. Because remember, this 2 by 4, for example, if you'd like to implement these midterms, for example, you also need AND gates, right? For instance, you got A0, A1, right? This says A0 prime, A1 prime. Okay, maybe I have to also have the inverted versions of A0 and A1, right? So you AND them. So that's your first midterm, M0. How about this one? A0 prime, A1. So you have to put in another AND gate, and then this one. And this says A0, A1 prime. You got this one, and then another AND gate, and you got the idea. You need 4 AND gates to generate M0, M1, M2, and M3, right? This is the 2 by 4 decoder, which is made of AOI gates. And on top of that, you got more AND gates here. So total number of AND gates is, you got 4 here, 4 here, right? 4 plus 4 plus 16 here, You've got 24 AND gates. Now, coming back to the previous description that I talked about, having the computer software do the job for you, probably you will come up with a circuit that uses less number of gates, because it's a more compact and joint optimization. This is a hierarchical design. The advantage of this design is simpler. We didn't, for example, draw any truth table, right? Big of truth table of that size, 16 by 20. We didn't, for example, execute any corner maps. We didn't do any optimizations. Of course, we will end up with more gates, okay? But hierarchical design helps you build circuits quite quickly. And the other thing is that if you got a problem, for example, in your circuit, such as this decoder doesn't work, you can actually immediately realize that this is not working, so you replace that, boom, you have got your design in hand. However, if you got one of the AND gates in the computer, generated circuit, and one of the AND gates is, not fail, for example, in that case, you have to first identify that AND gate, which is pretty hard to do because there are many, gates in your circuit in general. And after identification, you have to replace that AND gate. And that basically poses a lot of challenge in terms of design and implementation. However, here, it's much easier to track down the error as well as replacing the component, because this component is pretty packed and the design is not messy, right? It's pretty simple to see, and we know what's happening in terms of mean terms and the final outcome of the 4x16. Okay, let's come back to here. You got 5 by 128. What's your intuition on this? What would happen if I'd like to design a 5 by 128 decoder using simpler decoders like 2 by 4 or maybe 3 by 8, or maybe 1 by 2. 1 by 2 is not technically a decoder, but if you have to use it, maybe you can try. Okay? What would your guess be?
5 to 32 and 1 to 4.
1, 2, 4?
Yes.
The other one?
5 and 32.
5. You mean, 532. Okay, I see. So you got, this needs to be 7 then, right? This needs to be 7. Okay, so you're saying 1, 2 by 4.
It changes now.
I changed the question because 2 to the 7 it makes 128. It's not 2 to the 5. 2 to the 5 makes it 32, right? That's why. That's why. There was an error in the question. You want to revise your answer?
I will.
Okay. So this is 7 by 128 because 2 to the 7 is 128, right?
3 by 8 and 4 by 16.
3 by 8 and 4 by 16, says your friend. Okay. How about I use 2 by 4 and 5 by 32, for example. How about this? Actually, you can use any one of them, Either one of them will work. However, you would prefer someone that is closer. These 3 and 4 are closer to each other, right? You would prefer the closer one because that reduces the number of gates you use. Okay? In terms of these output gates. Okay? You can think about it and verify that. That's why usually what we are going to do in hierarchical design, let me move to that part of the board. Okay, so in general, so let me just erase. Okay, in general, we have K2 to the K decoder design. Okay, K to 2 to the K. K could be any integer. Okay, so what we're going to do, if 2 divides K, Okay, this is my division operation. 2 divides k. Okay. Then I'm going to use 2 q. This, let's just say k over 2 is q. Then I'm going to use 2q to the q decoders. Okay. Example. K equals, for example, 4. I've given that example already, right? So k equals 4 makes it, this is 4 by 16. And I use, since 2 divides 4, so I use actually q, which is 2, because 4 divided by 2 gives you 2. This is actually 2 by 2 to the 2, which is 4 decoders. Okay, and that's exactly what I've done in here, right? In here. How about k equals 5? This is going to be, again, this formula. You got 5 to 32. So I'm going to use the second case, which is k2 does not divide k. In that case, then k minus 1 over 2 divides k. So I'm going to call this q1. And k plus 1 over 2 divides k, and this is q2. If 2 cannot divide k, then k minus 1 and k plus 1, 2 will divide k minus 1 and k plus 1. Okay? So I'm going to call them q1 and q2. These are integers. So I'm going to use now 1 q1 to the q1 decoder, and 1 q2 to the q2 decoder. Okay? Again, I'll use 2 decoders, but the size of the decoders would be different. And now coming back to this example, okay, I use, since k is 5, right, and 2 does not divide 5, so just subtract 1 from 5, you got 4. 4 divided by 2 gives you 2. So 2 by 4, 1 2 by 4 decoder, and 5 plus 1, 6. 6 divided by 2 gives you 3. So 3 by 8 decoder. Okay, that's exactly what I just described, saying that these two numbers must be as close as possible to each other. Okay, to decrease the number of output AND gates. All right. Okay, so for that particular example, 7 by 128, we got these options here, and the option that gives us the least number of AND gates at the output is 3 by 8 and 4 by 16. Again, the general description, according to general description, 2 does not divide 7, but 7 minus 1, 6. 2 divides that number, and 7 plus 1 is 8, and 2 divides that number. That's why we have 3 here and 4 here. Okay? All right. Let me continue here. Now, we know encoder now and decoder. Decoder is pretty simple. Actually, simpler than encoder, because encoders has got this error mitigation problem in the inputs, right? And we talked about that a bit more complicated concept of priority encoder. But there is no such a thing in decoders. Decoders are pretty simple to describe, and most of the time we use hierarchical design for both encoder. You can actually apply the same hierarchical design idea to the encoders as well. Okay, so decoders are pretty useful because they help us implement functions pretty easily, because they give us the mean terms. So we collect the mean terms to be able to write the functional, the f function f, in terms of SOP form. Then you use decoder to implement it. Okay, one more thing about encoder and decoder, both of them, is the enable input. That you may have seen it in your labs. An enable input, basically, when you turn enable on, that means the circuit will operate. If you turn it off, then circuit will not operate. Okay, that's the idea behind enable. So let me just apply that to the encoder. we have decoder, A0, A1, this is my decoder. You got 4 outputs, right? D0, D1, D2, and D3, okay? And I've got an enable input here. Enable input is pretty simple to implement because all it takes is that you take the original decoder without enable, and all these are M0, M1, M2, and M3. These are the mean terms. And enable the input is here. All it takes actually, connect them to an AND gate. Okay, you got 4 AND gates, and all of these are going to connect to the first input of the AND gate. The rest of the inputs are going to be connected to the enable. Okay? It's that simple. Because whenever enable is 0, all of them would be 0. If enable is 1, then whatever these outputs are, they're going to be passing through them. So this is like a switch, right? Like a switch. So this is our design here. Okay? So enable input actually, from a Boolean expression perspective, all right, so M0 is A0, A1 prime prime, right? And M1 was A0 prime, A1, and this was A0, A1 prime, and we have A0, A1. Now we have enable inputs, let's say E, okay? So all you have to do is just AND E with these expressions. So you put an E in the front. Okay? These are the Boolean expressions of a decoder with an enable. With an enable. Sometimes you may be given, so let me also draw the truth table just in case you have it. You got A0, A1. It's pretty simple, but I'm going to draw it anyway. So you got 0, 0. Actually, let me draw this way. If enable is 0, A0 and A1 don't care. I mean, we don't care what A0 and A1 are. So these are all 0, 0, 0, 0. If enable is 1, then we take care of the rest of the inputs as 0, 0 would generate a 1, 0, 0, 0. If enable is again 1, then this is going to be 0, 1, 1, 1, 0, and 1, 1, 1. This is going to be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay? These are going to be the outputs in the truth table of the decoder with enable. So you may be actually asked a function, for example. You may be given a function f. A, b prime plus a, c, let's say. Okay, or maybe cb. Okay, 3-input function. And you may be asked to implement this function using a decoder with an enable. Okay? So you can actually use this functional form without thinking about what's inside. This is what is inside. You already designed this one, and now you see extra AND gates and then enable input, but you don't need to care about the internal design. All you have to take care of, just use this block as is. Okay, or if you'd like to put extra AI gates, around it, that's also fine. But the question asks you to use this block as is, okay, without worrying about the details of the internal design. So let's just look at this. First of all, you have to think about whether or not you would be able to implement this function using a decoder with an enable, right? That's the first question. Now, if you look at this and take in parentheses A, you got B prime plus BC, right? Well, enable, you see, is a common term to all of these inputs. So therefore, this A may be an enable. However, this is not in the form I like it to be, because this is not a mean terms, right? For B and C, of course. I mean, BC is a mean term, but B prime is not a mean term. So maybe I can actually make this look like 2 mean terms. How? Well, of course, I can use my postulates and theorems to write this B prime C plus C prime plus BC. You may actually get used to this already because you've already submitted your homeworks, right? So hopefully there's no problem here, right? So this is C plus C prime. Okay, so now I use distribution law, right? Why are you guys laughing? Isn't the homeworks was not a satisfactory submission for you? Haven't you done good in your homeworks? You haven't submitted homeworks?
The funny thing is your explanation, because we all did this, and you say, like, I don't trust you guys.
Of course not. I didn't mean that. What I mean is, since I thought, I assume that you already have come across this type of tricks in your homework. So
Yes.
you've already probably used it many times. So when I used the trick here, I just hoped that we didn't have any problem. So I don't need to talk about the details, right? But if you still have problems, okay, because some people here are silent. If you still have some problems going through these magical Boolean manipulations, please let me know, okay? Okay, so I got now a B prime C, right? Plus B prime C prime and plus BC. Okay, good. Now, A looks like an enable now, right? I mean, you can distribute it if you like. But I've got a missing min term here, which is
C prime.
BC prime, right? BC prime. Okay, now I can use the decoder. Let's just draw the decoder. This is my decoder. These are inputs, these are outputs, this is enable. I put A to the enable, okay? I know these min terms because I know this is going to be, if I put BC here, I got B prime, C prime here, I've got it, okay? So let me just take it. This is B prime C, I got it. This is BC prime, I don't touch it, okay? And I've got BC. All right, so I don't use this output. So I'm going to now OR them together, right? Because each one of them now is a B prime C prime, a B prime C, and this is a BC. And this is exactly what I'm looking for, okay? So I finally get my F function. Okay, using a decoder with an enable, and I put these inputs to the, I don't need to worry about now the rest of the internal design. Are we good?
Yes.
Okay. Okay. So see, I didn't even bother drawing a column map, right? Although it's a 3 inputs case, 3 input case requires 2 by 8 column map. Okay, things are getting a bit more complicated compared to 2 by 2 column map, right? So therefore now you actually skip that process using simple Boolean logic and a decoder with an enable, okay, with an OR gate, okay? Isn't that beautiful?
Yes.
Okay, great. I'd like to think about this decoder. I want you to think about this decoder and look at it from a different perspective now. Because I'm going to just turn this around, okay? Now this enable is going to be here. Okay, I'm actually turning it to a clockwise direction, okay? And put this enable here, and A0, A1 here, okay? And maybe I can draw the A0, A1 at the bottom because that's what we usually use, okay? So A0, A1 here, and these are the outputs, D0, D1, D2, and D3, okay? When I see an enable 0, I don't care about the A0 and A1. I actually see all of them are zeros, okay? This is the same circuit, by the way, guys, okay? I didn't do anything magical yet. It's just the same thing. I actually turn it around. Okay, what happens when enable is 1? If enable is 1, okay? I see a 1 at D0 if A0 and A1 is 0, 0. 0, 0, I see actually this 1. So this just like, I'm pushing this 1 to the D0, right? But the rest of them are zeros. So it's just like you're pushing 1 to the D0. Why am I saying that confidently? Because if enable was 0, D0 was also 0. So therefore, I'm pushing this 0 to the D0. So that logic of pushing something to a specific output, okay, is a good description of what's happening here. Because if you look at the enable is 1 and A00, A1 is 1 case, you will realize that now I'm pushing this enable 1 to D1, right? So this is like a switch now, right? Enable being 0 or 1 doesn't matter. You're going to be, by selecting the appropriate inputs, A0 and 1, 0, 0, 0, 1, 1, 0, 1, 1, you're actually choosing a path for this input. Okay? You're basically selecting a path. For example, if something coming into the circuits, 0 or 1, doesn't matter. Okay? If you select 0, 0, then whatever you see in the input will going to be reflected to the 0. Okay? And if A0 is 0, A1 is 1, or A0 is 1, A1 is 0, then you're selecting either one of these. Or A0, 1, A1, 1, in that case you're going to be selecting this path. Because whenever you see a 0 or 1, that would appear at the output D3. Okay? This is actually a reverse operation of mux operator. Do you remember the mux multiplexer? This was actually the reverse. So this is called demux operator. Okay? Demux. Okay, because it's basically turning the functionality, all in reverse direction. In the mux operation, if you remember, there were 4 inputs, and you select one of them to pass through the output. The rest of them are just, limited. They're not allowed to pass. However, in demux, you got only one input, and you select that input to be forwarded to. Okay? You either forward that input to the top output, or the one that is below it, or the one that is below it, or maybe at the very bottom of the outputs. Okay? So that's exactly the reverse operation of mux. So what I'm trying to say here is that decoder enable with an enable is nothing but a demux operator. Okay? If you need a demux operator in your design, just use a decoder with an enable, because it's exactly the same. Okay? Okay, now you learned about multiple things. You learned about muxes in our previous classes. Now you learned demux. You learned encoder and decoder and their enable inputs. Okay? These are perfect combinations of very frequently and commonly used set of combinational logic. Okay? I mean, I cannot think of any logic without these components. These are everywhere. Again, one more thing I'd like to emphasize that, because it has to stick into your mind and stay there forever. You may come up and say, well, we learned about AI gates, we learned about NAND gates. Why are we caring about these, weird components? Well, the thing is that people have stumbled upon these circuits many times. I'm talking about engineers, by the way. They devoted a lot of time optimizing them. In the transistor level, not the gate level, by the way, okay? The transistor level, meaning that in nanoscale, they actually come up with a lot of optimizations. So therefore, these designs are super optimal. So if you think about this question, and if I want you to design this circuit by using straightforward logic, using AI gates, what would you do? You would have A, B, C, and they're not gates, right? And then you go A, oh, I have an A, okay, good. I have B prime, okay, now connect them, and, right, you would do this. This is exactly the standard way. But you would come up with a more complex operation compared to this one, because this would use less number of transistors. That's why I designed it this way, because it's more efficient than this, because this is super optimal. Okay, in the transistor level, of course. Okay? For the sake of this class, we're always doing this Carnot maps and common term and 2-level optimizations we learn. These are all gate level optimizations, not transistor level optimizations. Okay? And this is not, the transistor level optimization is out of scope of this class. That's why I'm not teaching it, but just know it, because it's connected. Okay? We cannot isolate these classes. I cannot isolate this digital system class from an electronics class. Or I cannot isolate this class from a computer architecture class for computer engineers. Okay? These are all connected classes. Okay? If you're learning one of them, you cannot isolate it from the other. So I'm just opening the door for you. There's a gateway to the electronics, physics. Okay? Just know it, but that's what I'm going to say the last. Okay? All right. Finally, now I'd like to use all of these components to implement the functionality. Okay? This is the first beginning of the functionality. It's really simple. I also taught you how to implement the function using mux, right? I also shown that. Good. So you know how to implement the function using a multiplexer, and you know how to implement the function using a decoder. I think I've got an example there, simple example. And you know how to, for instance, if I didn't give you a decoder with an enable, okay, let's just use only decoders and they don't have any enable. Can you implement this function using a 2x4 decoder?
Yes.
No. Why? Because you got 3 inputs and 2x4 decoder has only 2 inputs. The reason that we're able to do that with this decoder because there's an enable functionality that we can push the third input to that so that we can get this functionality. But if you got no enable, then you cannot use this decoder. Instead, what would you do? You would use 3 input decoder and 8 minterms, and then figure out the minterms here. For example, you got 1 minterm here and 2 here. So there are going to be 3 of them all together to create that functionality. Okay? But this would be a bigger decoder because there is no enable inputs. Okay? Here, we've got an enable. For example, if I said, let me also give you another example, all right? So if I said f equals, not this one, but a prime, b prime plus a, b, c. Okay? Can I use a decoder with an enable to implement this?
Because we have a.
Let's write it more explicitly using minterms. This is a prime, b prime, c plus a prime, b prime, c prime, right? This one. And there's a b, c. Okay. Can you see a term that is common to all of them? No. So therefore, you cannot implement this function using a decoder, 2x4 decoder with an enable. So the only option for you is to use 3x8 because that creates all of the minterms. This helps you create only specific minterms. Actually, if you group them together, you either implement that start with a or a prime because you can also push an a prime here. Remember? But here, you got a and a prime. You got B and B prime, you got C and C prime. That's why you cannot implement this using a decoder with an enable. Alright? Okay, so just know that, I mean, you're trying to reduce the number of inputs because this enable is not going to complicate your circuit. So you're trying to reduce the number of gates by using a simpler, smaller decoder, but that doesn't always help you. Okay? Just keep that in mind. Okay, there's a trade-off here. You're trying to minimize your circuit. Good. But you would like to have a complex functionality because you want to do more things with your circuit. But here is the trade-off. Right? And your job is to figure out a good hotspot where you have simple circuit design and more functionality. I mean, as much as possible, of course. All right, final thing is implementation of a function using all these components, encoder, decoder, mux, demux, whatever is needed, okay? Because now I'm going to come back to, I think you all have taken Java class, right? Or a programming class. How many of you are computer engineers? Well, most of them, okay. How about you guys? Did you take any programming classes?
Yeah.
Okay, good, all right. So I'm going to now talk about a conditional statement that you have implemented using ifs, right, in your programming classes. Now you will do it in the hardware level. Because that's exactly what's happening. When you write an if on the very, let's say, in the orbit of the Earth, that if actually gets translated into, many times, something that is friendlier for the hardware, right? That is the surface of the Earth. That's the reality. Okay?
What about for?
What?
What about for?
For loops, we can also implement that, of course. Everything that you're able to do in the orbit, when you come down to the surface of the Earth, has to be implementable. Otherwise, it will never be a reality. Okay. Here is my function. I'd like to implement f equals. Oh, let me give you. Okay, let me give you a simple function first, and then a bit more complicated one. This conditional statement will come later. So I'm going to actually come back to this specific. So I forgot to tell you about one more thing about this example here. Okay, which is that this uses 3 inputs, right? I mean, this mean terms, right? All of them. Well, the thing is that these 3 mean terms actually can be rewritten. Let's look at this example. So you see these are 3 mean terms, right? These 3 mean terms, there's a relationship between these 3 mean terms and the rest of the other mean terms, which is this one. Can you see that this one, let's just say this is G. And this mean term is A, not A, but maybe this will not work here, maybe, but anyway. So the mean term here, this will not work here. The reason being, what I'm trying to do is, let me just tell you what I'm trying to do. This actually, these 3 mean terms, is nothing but BC prime prime. Why? Can you tell me why? Say again? Yes, that's right. But what I'm trying to do what I'm saying is, these 3 mean terms equals to this. Why is that?
Consensus theory.
No, it's not consensus theory. It's a good try though, good try though. But no, it's not. But yeah, think about this in terms of truth tables, okay? So if you look at B and C, let me show you what's happening. And let's just say F function. Let me just G function, sorry, G function. I already gave a name. 0, 0, 0, 1, 1, 0, 1, 1. I've got these mean terms, right? B prime, C, B prime, C prime, and BC. So this is 1, 1, 0, 1, right? So how about G prime? If I ask you to fill up the truth table for G prime, you would say 0, 0, 1, 0, right?
Yes.
It's exactly the flipped version. All right. So if this is G prime, what is G prime in terms of mean terms? What is the mean term here? C prime, right? BC prime.
Yes.
So if you take the complement of both sides, G would be equal to BC prime prime. It's exactly what I'm saying. Okay? So, of course it would not work here. Why? Because we didn't have A. Okay? Forget about A. So the function would change, of course. Function would be, I'm thinking about only G, right? Then instead of ORing these 3 inputs, I'm going to just put a NOT gate here and then push it out, because that's exactly identical to these 3 mean terms. It will not work here. Why? Because A also comes in with that input. If you negate that or invert that, A will also be inverted, but A is not part of your function. That's why it's not going to work here. But if we had